So I showed you we always have convective movement in a cell, and we need a second derivation of our momentum quantities u, v, w, and the Mr. Navi and Mr. Stokes formulated their equation based on the idea of diffusion. In nature, this effect is much more complicated. You will have also swirls and turbulences, but to make it a bit more simple, you can formulate it with a diffusion effect, and this diffusion effect also really happens in nature or in technical problems. For example, to describe it a bit better, I have some examples. Here you see, for example, you can see there is that picture was made with a pen. Yeah, they took a magic marker or a pen with red color, and they put it in water over a sheet of paper, and now if the ink from the pen or the paint from the pen is mixed with the water, and then you will have a convective movement of this ink, of course, but you will also have a diffusive movement of the ink into the direction 90 degrees to your convective direction. Same effect is you can discover the same effect if you have a cup of tea or a cup of coffee or a glass of water, and you put a lump of sugar inside the water, and even if you don't stir it, even if you don't mix it with your spoon, the sugar after some time will be dissolved in the whole glass of water, and this happens by the effect of diffusion. You have the sugar molecules, you have your small dice of sugar or a small lump of sugar, and if you put it into the water, even if there's no convective flow, no mixing, the sugar will be driven by diffusive flow. Yeah, it will diffuse into the water, and after some time the whole water is mixed with sugar, even if you don't stir the water. Yeah? And how can this happen? This happens by the effect of diffusion. Every sugar molecule or every particle from the paint of your magic marker in the water, it will travel and it will move. Yeah? All the molecules, the paint molecules or the sugar molecules, they always move, and even the water molecules and the air molecules will move and it is driven by the so-called Brownian movement of the molecules, and this movement is really fast, but it's not in any special direction. The movement will act in every direction, in nearly every direction. So you can't describe you can't say we have a molecule here and after 2 seconds it is 2 meters away. Yeah? So we can make a first derivation of the velocity with time. So we need always a second derivation, because movement will not be in any special direction. Huh? So for this is another example for driver for diffusion. If you can imagine, we have our molecules, sugar and water molecules in our glass, and then we put it in a bigger glass of water without any sugar, all the molecules of the sugar will be spread also to the areas where no sugar was before. Or if you can imagine, we have here a glass with molecules inside, and the molecules move, they push each other, and then if we open a wall in between and we have less molecules, and the other side the molecules from this denser solution will travel into the other parts of this glass. So molecules always try to move from areas with high concentration to areas where the concentration is smaller. Okay. And this effect was also described by famous scientists, and maybe you know I always like to tell you something about the scientists who invented this effect. And one famous scientist who described this effect was Warren Kendall Lewis. He lived from 1882 to 1975, and Lewis made a lot of work in this conductive and diffusive flows. He described a lot of effects of diffusion, and he also explained it with the viscosity, with the turbulent, with the dynamic viscosity. And because of his work, number was called after Mr. Lewis, and the Lewis number is described by the Schmidt number over the Prandtl number, and more or less you can to describe it in a more simple way what the Lewis number means. If you have a Lewis number from 1, you have two different fluids, for example air or methane, or air and nitrogen, which have different molecule sizes. And if you have a Lewis number from 1, the air can diffuse in the same velocity as the nitrogen can diffuse back into the air. If you have Lewis numbers different from 1, the diffusivity between two different gases or two different liquids is different. Okay, it's a bit complicated. You only have to check these Lewis numbers if you want to mix different gases, and if you want to know if some gas can diffuse faster into another gas. It can be, maybe keep this a bit in mind, because you know we want to shift from all the mineral fuels more to hydrogen. Hydrogen is a really interesting alternative for fuel for cars, and hydrogen has really small molecules. It has the smallest molecular weight of all the molecules, and now because of this, the molecule can diffuse really fast. If we have air here, for example air in this room, and we have some small hydrogen molecules, they will diffuse much faster into the air than the air can diffuse back into the hydrogen. Now you can say, okay, this can cause really big problems for ceilings and for valves. If you have ceilings, if you have a car with hydrogen in your garage, and the hydrogen can diffuse really fast, it will diffuse into the garage, and then problems can happen. You can have explosions. But on the other side, because of this really high diffusivity of hydrogen, I think the danger gets smaller, because you won't have it will also diffuse really fast out of your garage, for example. If you use methane gas or propane gas for your car and you park it into this garage, the diffusivity is much slower than if you compare it with hydrogen, and this can cause bigger problems because you can get like bubbles of methane in the garage, and then if you get a spark, you get problems. Okay, though more or less enough about this now. That's a so-called Lewis number, and here we have also an example of diffusivity, of the velocity of the molecules, and I told you hydrogen, a new really fancy fuel for cars. I think in my opinion is hydrogen will be the next generation after the electrification of cars. Now we have some, of course, we have some good electric cars like Tesla, for example, but the next step should be hydrogen, the hydrogen car, and because that's really we don't have any carbon dioxide if you use hydrogen cars, and the diffusivity of hydrogen is really high, so we will get some problems at the ceilings, we will get some problems at the walls, we will get more diffusion problems because the diffusivity is so high. Hydrogen could even diffuse into metal, into steel, and could destroy the steel, so we need new designs and new materials for our valves and pipes inside the cars. And if the molecules get more heavy, for example, if you have carbon dioxide, which is a really heavy molecule, and it's a slow molecule, yeah? Okay. Now, maybe you can imagine carbon dioxide. You don't see it, you don't smell it, but if you can imagine you have a car and you use your car with normal gasoline, mineral gasoline, or diesel fuel, all the diesel fuel and all the gasoline that is inside your tank, if you have a tank of 70 kilograms or 100 liters, you have more or less 100 kilograms of gasoline fuel, and you will have the same amount of carbon dioxide and water that has to exit the exhaust duct, so you don't see the water, you don't see the carbon dioxide, but you can imagine it will be a big amount of gas. And these gases are rather slow, so they will stay, the molecules are big, and they will, diffusion will be much smaller than the diffusion of hydrogen. And if you can imagine the simulation of my jet pictures, if you can imagine, if you remember the jet pictures of the nitrogen, you can imagine if I change the gas, if I use hydrogen or carbon dioxide or water gas, you will have different kind of jets. They will look different because the diffusivity will change based on changing molecular velocities and molecular weights. So for every gas you have to design new nozzles or new valves. Okay, and here's a more classical description. We always use NCFX. We describe the movement with a Navier-Stokes equation, but an older form of the Navier-Stokes equation is the so-called Fick's law, but it describes the same effect. It's just a little bit more easy. You can describe the amount of molecules, the number of molecules based on a diffusion coefficient multiplied with the derivation of the concentration into convective direction. So more or less, that's an easier form of the Navier-Stokes equation. And if you want to charge your simulation results with ANSYS CFX, you can take Fick's law and compare it. Yeah? And this law is quite older. Yeah? It's named after a German scientist Adolf Fick, and here's a German newspaper article from German newspaper about it. If you like, you can refer to the slides and read it. He formulated the Fick's law in the beginning of the 20th century. Okay. Here's again some description, but we don't really need it here. Fick's law, you will only need it if you want to check your CFX results on a sheet of paper with a pencil, but more or less the description with the Navier-Stokes equation is much more reliable. Okay. Here's another effect where you can see diffusion. I gave you the example with a lump of sugar, and I gave you the example with a magic marker ink. And here you can make also a new experiment if you have a glass here and we put some ink inside or some particle, even if you don't stir the glass, if you don't mix it, you have no convective flow inside the glass, everything is calm, you will have this diffusion movement of the particles. Okay. And there's another experiment where you can see the effect of diffusion. Yeah. For example, if you take some beans and you put water in the beans, and maybe you can go to your kitchen, you can do this experiment on your own. You place them on a table. What will happen? The beans will grow. And this is also driven by the effect of diffusion. The water outside the beans will diffuse into the beans, and you will get bigger and bigger beans. Okay. In nature, this effect is described by the effect of osmosis. Okay. So we have an analogy between fluid flow and diffusion. Yeah, we have volume transport and species transport, and both are diffusive effects. Okay, so you will see also Fick's law can be formulated in different direction, and if you look closely at this equation, they look really like our Navier-Stokes formulation of the diffusive term. So the formulation of Fick's law into three directions of a Cartesian coordinate system is the same term as the diffusive term in the Navier-Stokes equations. Okay. And last but not least, I want to mention also the so-called Kolmogorov theory. The Kolmogorov theory will be described in more detail a little bit later in our chapter Turbulence, and I try to explain it. You can imagine you have convection and you have diffusion. And diffusion is a physical effect where you have non-directed movements of molecules in every direction. Yeah, it's convective is direct movement into one direction, and diffusion is the second derivation of this movement term. It's in any direction. And what happens if you have a swirl? Yeah? If you go back to a picture of the airplane and the swirl behind the wing, the swirl at first it is big. You can describe it with convection. Yeah? With a convection movement, you can describe the swirl. But it gets smaller and smaller and smaller and smaller. And at some scale, the swirls are so small that the convective movement of the smallest swirl is smaller than your diffusive movement. And that's the so-called Kolmogorov scale, when the convective swirl gets smaller than your diffusive. So the convective movement inside the small swirls gets smaller than the diffusive movement in the small swirls, and then they disappear. And that's the so-called Kolmogorov scale. And of course, every fluid has different type of Kolmogorov scales. And you have to know them, you have to know how big the Kolmogorov scale is, and then you can choose the right turbulence model for your case. Okay. And yeah, there are a lot of different formulations for diffusion coefficient. That's also another lack in where the turbulence models are, the quality is not so big. In CFX, when we make the simulation of our airplane, we always will have constant diffusion coefficient to calculate the diffusive terms. Yeah, we make the second derivation of our velocity, we multiply it with our diffusive term, and then we calculate our diffusive amount of the fluid flow. But in nature, this is a bit more complicated because the diffusion coefficient is a fluid property and it is not linear. It's just a model that we use linear behavior of the diffusion coefficient. Normally, the diffusion coefficient will be non-linear, and this will make the mathematical formulation even more complicated.